Can this boy huff, puff, and blow this tube down? Find out next on Mr. Wizard's World.
Stacy, I've rigged up all these little lamps. In each one of them, there's a 100-watt light bulb, because today you and I are going to do an experiment that has to do with how much electricity you use around the house when you plug in various things. But first, I have to make sure you understand, what is a fuse?
Well, I know we have them in our homes because one time we put too many things in one socket and it blew. My mom said it blew a fuse, so she asked me to go downstairs and flip a switch.
Mm-hmm. And you did, and all the lights came back on again.
Right.
Well, that was probably a circuit breaker that works on the same idea. When too much electricity goes through the circuit breaker or the fuse, it heats it up and burns it out, and that's why they say it blew a fuse. Okay.
Right.
Well, what does the word fuse mean, you know?
No, I don't.
Well, have you ever heard of two metals fused together?
Oh, yeah,
Yes.
like in welding.
Right. Okay, what fuse really means is burn or melt. And
Okay.
here's the wire that's going to melt. See that little wire that goes from there all the way across over there?
Yeah.
Okay. Here is a master switch. When I turn it on, that red light means electricity is now going through that wire, down over here through wires, and to every one of these light bulbs.
Okay.
So what I want you to do is start over there with light bulb number 1 and turn it on and keep a close eye on what's going to happen to the fuse. In fact, I'll put this little piece of paper on the top, and that may give you a clue right away. Okay. Turn on the first light. 100 watts.
200. Still nothing's happening. Number 3, nothing. 4, 5. Oh, it's starting to smoke. Oops.
Yes. 5, at least you can tell the wire's getting hot, right?
Yeah.
Okay, try 6.
Paper's gonna drop off pretty soon. Oh, and the wire's getting red.
Yes, just barely getting red.
Do
Keep
7.
going. Here comes number 7.
Number 8.
Now, you see it's really red, like in a toaster, right?
Yeah, and it's sagging now.
Yeah, it's sagging. Here comes, what, 9?
10.
10.
Oh, it's getting low.
It's a good idea to wait just a little bit, Stacy, because it takes a little while for the wire to heat up.
Okay.
Okay. So now 11.
Now 12.
Try 12. Ooh, it really sagged.
Should I do 13?
Well, wait just a minute at 12.
Okay.
Because the wire's getting hotter and hotter and hotter.
Oh, it just dropped
and finally
off.
dropped off. Now I can turn off the master switch so there's no danger. And you
Okay.
turn off all the light bulbs. And I'll put in a new fuse. Because now we've established a sort of unit of electricity.
Okay.
Right?
Because we turned on 12.
12 light bulbs, right.
There we go.
Now, take out one of those light bulbs. Take the top right off.
Which one? This one?
Any old one over there.
Oh, this top came
And
off.
there's a little black thing like this. You know what that is?
Yeah, I do. It screws in here,
Right.
and then you can just
Okay.
plug in and you can get
And you
electricity.
plug in anything. Okay.
Right.
Well, I
Okay.
put in a new fuse wire. Okay, now you see over there, behind thing, there's an iron.
Oh, yeah.
Okay, well, you bring that up, and you know what we're going to do with it.
We're going to plug the iron into this.
Right, we're going to plug the iron right into that. Now, remember, our unit of electricity is 12 light bulbs.
All right.
Okay? The reason why we're doing this is not only to burn out the fuses, but to find out when you use the most electricity around the house. So far, we've changed electricity into light. When we plug in the iron, we're going to change it into heat.
Okay.
All right? First, the master switch. Okay. Now, you have to throw that switch to turn on the iron on.
This switch?
Right.
Oh, look how fast
Look.
it's going. I don't think we need to turn on a light bulb.
You don't think so?
No. Well, maybe one.
Maybe one.
I'll turn.
That's
Turn on number 1. Maybe 2?
Okay, try 2. There we go.
It's going to go
That's
on
about
2.
the same as it was before, right?
Yeah.
And if we let it sit there for a minute, it should say...
Maybe we should
and
turn on 3. Oh, no, we didn't need to.
Okay. Now I'll turn off this
When
master switch.
that went off, the light bulbs went off too.
Yes, because, well, wait a minute. Why was that a surprise to you?
Well, I thought, I don't know. I just never noticed it before.
It was the
What we did
fuse for all these
before.
light bulbs. That's why it went out, just like in your house. You know, what have we found out? In
Well,
terms of light, 1 fuse worth of electricity was equal to how many? 12 you turned on.
Yeah.
Okay.
And if you put an iron in, an iron is worth equal to 10 light bulbs.
10 light bulbs, yes.
100 watt too.
Yes, 100-watt light bulbs. Therefore, every time you change electricity into heat around the house, you're using the most electricity.
Right.
So therefore, use it as quickly and as efficiently as possible.
Yeah.
Billy, you're looking at a very unusual material.
What's so unusual about ice, water, steam?
What's the temperature of the ice?
The ice is 0 Celsius.
Right. And the temperature of the steam inside the kettle?
Is 100 degrees.
Yes. And what's the temperature of the water?
Anywhere in between.
Well, that's the important thing. Nowhere in the rest of your life will you probably ever deal with a material in which within those temperature ranges it will be a solid, like ice, a liquid like water, or a gas like steam. These are red blood cells that carry food and oxygen to all parts of your body. They were photographed with a light microscope. They're very small. 3,000 of them side by side would measure only an inch. Yet in this picture of one cell, you can see amazing depth and detail. That's because it was photographed not with light, but with electrons. You see, a beam of electrons on the left scanned the cell, while a similar beam in step on the right scanned a screen, something like a television picture tube. Each point on the cell was represented by a corresponding point on the tube. Of course, all this happened at very high speed, line after line of information combining to form a complete picture of the cell. You can see why the instrument is called a scanning electron microscope. Scientists have used the instrument to take a closer look and get new information about all sorts of things, including the red blood cell. Well, Jason, I can see from the screen that you've programmed logo with a program called Try. What's Try?
Well, Try is a program that'll draw a triangle on the screen.
Okay, how do you do that?
Well, I'll run it right now. Try, enter, and there's a
Okay,
triangle.
so I made a triangle. So that's your little program called Try.
Right. Now, I'm going to draw a larger triangle. So, punch in repeat
Repeat.
3 times.
So,
Now, gotta make the brackets and forward. But this time I'm going to make it go 50.
Aha, okay.
Right turn 120.
20.
And we'll try that. And you can see it.
Oh, yeah.
Larger
made a
triangle.
Larger triangle.
Right.
So all you had to do was change one thing in in the little program, and
Right.
it did it. Right.
Now, the problem with this is that you have to keep typing things over and over again to make bigger triangles. So I'm going to edit this to make it a lot easier to make bigger triangles.
Oh, okay, great.
Okay,
So ED, I assume, is edit,
edit,
and there's your program called Try.
try.
Okay.
Now,
Now you're in Logo Editor.
right, now
There's your program. Now what do you do?
we're going to try something called variables.
Yes.
A variable will let you change stuff. Like it gives the computer a bit of a choice on what it wants to do. So,
Oh, I see. The computer's going to wait for you to tell it what the variable is.
right.
Okay, where you put the variable.
Now, as we said before, it's harder to keep changing this over and over again. So what we're going to do is we're going to take out, see where the 30 is? We're going to take that out and put a variable in there.
Okay, how do you do that?
Okay, well, first of all, we've got to tell the program that it's going to have a variable in it.
I see.
So we're going to put in, okay, we'll call the variable sides,
Yeah.
because that's what the variable is going to be for. or side to make it
Do
easier.
you have to put a colon in there?
Yeah.
Okay.
Okay, I'll put like that.
That's what I remember, yeah. Side. Okay, that's
Okay.
the variable.
Right.
Right.
Now we'll get down inside where the 30 is,
Yes.
and we'll put that variable in.
Okay.
Okay.
So it's
Side.
S-I-D-E.
Right. And we'll take out the 30. There.
Okay.
Okay.
Now you have a new program called try colon side.
No, it's still called try, but it knows that it has a
okay.
variable in it.
Okay.
Okay.
Now
so
what do you do?
we'll push escape and get back to the screen. Okay, see,
Okay,
try
try
define,
define,
so it
right.
knows what it is.
Okay, so now how are you going to put the variable in?
Well, first of all, we'll clear the screen.
Okay. There comes little turtle.
Okay, now we're ready. So I'll punch in try. Now, since it's got a variable in it, we have to tell it how big we want it to be.
How big are you going to make it?
Well, we'll make it 30 again this time.
Okay.
And see?
There it did 30, just
Now
like
watch. Instead of typing out the whole line, we can just change it by punching in try.
that. Okay.
We'll try 50. And so it's a whole
okay.
lot easier than typing out a big long
Sure
line.
is, because you have a variable in there.
Right. Okay, now we're going to try something really neat.
Oh, yeah?
This is a
What's
program I made using the
Yeah,
same
what's
kind
this?
of concept. It's called Spiral.
Spiral.
Okay, so we're going to have a little 2-unit line, and it's going to, on the next line, it's going to be 2 little units bigger, so that'll be 4. The next line, it'll be 6, then 8, and so on.
And it'll keep going till you tell it to stop, I'll bet.
Right.
Okay, let's see what
try
happens. There we go.
I added some color to make it more interesting.
Ah, look at it.
Isn't that
It's
neat?
it's way up to maybe 20 by now, right?
Uh-huh. And as you can see, it gives you a spiraling effect.
Can you get rid of that thing up there?
Oh, sure I can. There you
Ah,
go.
very good. How many eyes does a grasshopper have? Well, you can't miss the 2 large eyes on each side of its head. They're called compound eyes because they're made up of many small lenses. Etymologists believe the compound eyes detect movement, but can focus sharply only on nearby objects. But the grasshopper and many other insects, in addition to the compound eyes, have 3 other simpler eyes that are sensitive to light and dark. How the insect uses them is a mystery. So how many eyes does a grasshopper have? In all, 5. See that track right there?
Yeah, I see it.
Yeah, that's a dog track.
Really?
Yeah, I'm pretty
Oh.
sure it is, because what I did
Yeah.
was found this gopher hole and I put some water on it, had a dog run across it so we could get a good track. So I can show you how when you go out into the woods and you find a nice track of an opossum or a beaver or something, you can make a plaster cast of it and take it home.
Oh, okay.
Here's what you do. First you get out of, this is a piece of file folder, and you make it so it's just slightly bigger than the cast, or than the track, and then you can push it down like this, so you make a little fence around it like that.
Okay.
Okay. Now we have to make here's some plaster of Paris. Put about 4 heaping teaspoons in
4?
that.
Okay.
Have you ever seen plaster of Paris before?
Yeah, I had it put in my mouth one time at the orthodontist.
Mm-hmm. And you've heard of people that have broken their legs and have to have it in a
Yeah,
cast.
on a
Well,
cast,
that's what they
yeah.
make it out of.
Oh, I didn't know that.
Yeah. Put in 2 more.
Okay.
What you have to do is try to gauge how much you're going to do depending on the size of the track.
Okay.
Okay. Now let's get that.
Here's
Oh,
the
keep the
spoon.
spoon because I want you to stir it.
Oh, okay.
As I add a little water.
Okay.
Okay, stir it up. What you want to make it is about the consistency of sort of whipped cream,
Oh, yeah, sort of.
or maybe a little thicker than that. Maybe
Okay.
like. Okay, now we got to add a little
Bit
more
more.
of this. You keep stirring.
Okay.
Try to get rid of all the bubbles.
Okay. Yeah, it's
Okay,
getting
get it
thick
nice and-
now.
Now it's getting a little thicker.
Yeah, and plaster.
Just a little more.
Okay.
Stir it up. There you go.
Okay.
Okay, now carefully pour it right inside that little fence.
Okay, here's the spoon.
Okay, go ahead. Pour it in the fence.
All of it at once?
The whole thing. Just pour it
Okay.
all over. Great.
Oh, it's kind of mushy. It is
Yeah.
kind of like mud, too.
Okay. Now, while it's still wet, I'm going to put this paper clip bent up like this, right like that.
Okay.
Now, that's going to get hard. It'll take a while. And what happens when it gets hard, it'll hold onto that paper clip, and now you can hang the finished track on your wall.
Okay.
Also, when it gets a little harder, you should put your name and the date and where you found it, as you're going to make a collection.
Okay, I'll do that.
Now, when you find a track that you don't know what kind of an animal it is, what you should do is have a book like this, look.
Yeah, Pocket Guide to Animal Tracks.
Yes, and here you'll find all the animals that you might find out in the woods. Muskrat, mink, beaver, porcupine, fox. And you look for them along streams and ponds where there's nice mud where they leave a nice track.
Okay.
Bobcat, Canadian lynx.
Cougar.
Yes, badger,
Badger.
weasel, deer.
White-tail. Black-tailed
And notice they don't have dog, because these are all wild animals.
Yeah, they're wild animals.
Okay? So we'll let that sit there for a while.
Okay.
And when it gets nice and hard, you'll see a beautiful track.
Yeah.
Okay, check it with your finger, Tana, see if it's hard.
Okay. Yeah, it's hard
Okay,
enough.
now take the spoon and dig underneath it. So you pick up the whole track, dirt and all.
Okay.
Aha. Okay.
There we go.
Yeah, can you just bring the whole thing over here to the bucket now?
Okay.
Very good. Now I'll take this off. Now let's get off some of the major part of the
Outside
dirt. Okay, now let's put it in the bucket and wash off as much as we can.
Okay. Okay. It's almost off.
Well, here, let's take a look at it. Because later on, you can clean it up real good. You could even paint it. And there comes the track of a dog using Plaster of Paris. And you can make a whole collection of wild animal tracks. Eugene, you got your sleeves all rolled up, ready to go to work, right?
Yes.
First problem for you is pour that glass full of air into that one.
Okay.
Did you?
Looked like it. I mean, at least it. I don't know.
Well, the first place, air is invisible, right? So that you can't tell where it's happening. Well, before you leave today, you're going to pour air from one glass to the other.
How do you do that?
Well, first of all, I'll give you a clue. Here's a bottle full of water. Turn it upside down and watch carefully what happens to both the water and the air.
Okay.
What's happening?
Well, as I pour the air out, tiny bubbles of air goes in and then
Right.
push the water out
In fact,
again.
every time you pour a liquid, you're pouring air at the same time. Because in order for the liquid to come out, air has to go in. And that's the secret of how you're going to be able to pour air. You're going to do it upside down. Take a
Okay.
glass in each hand. Turn that glass upside down and fill it full of water. Okay, now, hold it so the mouth of the glass is just under the surface. Pull it up like that. Now turn this one upside down and fill it full of air. Pull it right straight down like that. Now bring it one over to the other, carefully, slowly. Oh, you lost some. Slowly tip it. There you go. Now you're pouring air, right? You're also pouring the liquid, aren't you? Because the liquid's going into the bottom glass. And notice the liquid's coming out of the top one. Keep going. You're not quite finished yet. Almost. Keep going. Get the last little. There you go. Now you can pick the glass up in your left hand. It was full of water. It's now
Now it's empty.
full of air. Ah, what?
It's empty.
No, it's full of air.
Oh my. Got me there again.
This plane has very important passengers aboard, brought here at the request of the state government. Here they come now. River otters. More than 75 otters have been transferred from Michigan and Wisconsin to rivers in Colorado by the Colorado Division of Wildlife. Because otters can migrate miles from where they are released, the biologist implanted a tiny radio transmitter in one of the otters. They can follow its movements by tracking it with a directional antenna on their radio receiver. An otter is an excellent swimmer. When it dives, Special muscles close off its nose and ears to keep out water. Otters had become nearly extinct in Colorado because streams in which they live had become polluted. Many had been killed by beaver trappers 100 years ago. But now these problems have been solved. Because of restocking programs like this one in Colorado, the next time you're out in the wilderness, you have a better chance of seeing the playful river otter. Jason, I have a challenge for you. See, I have a heavy book hung by strings from the swing here.
Okay.
And here is a paper tube, just barely balanced. What I want you to do is to knock over the tube using the book and a straw, but you can't touch the book with a straw.
Can I touch the book with my hand?
Nope.
Okay. Can I blow out the book?
Sure.
Okay.
Go ahead. Why are you blowing when you are at that particular time?
You mean like in beat?
Yeah, you don't blow all the time. You only blow in puffs. You seem to be timing your puffs.
I don't know. It just kind of comes naturally,
Yeah,
I
it
guess.
just seems like it. Well, if this were a child sitting on a swing and you wanted to push the child further and further, when would you give them a push?
Probably just as they're just going forward.
Again, right. Well, what you're using is a scientific principle called resonance.
Resonance?
Yeah, have you never heard that word?
No.
Well, it's the idea of something being in step. In the music world, for example, a resonator is the box underneath the string, for example, in a violin. If you can get the box to vibrate in step with the string, then the sound will be much louder.
Amplified.
Right, amplified. So that's what a resonator does. They also use it in many other fields of science. They also, in the Army, when people are marching and the soldiers are marching along in step, they're in resonance, and that little tiny step, if everybody's at the same beat, could add up when they got to a bridge.
Oh, and then the bridge would crack and it might wash out or something.
Well, it might. Anyway, they have a special command in the Army to break step so that won't happen.
So they just walk however they
Everybody
want.
walks there, so they don't build up that energy because they don't want to be in resonance at that point. So you're going to use the principle of resonance, give the book a little gentle push at the right time, and eventually knock over the paper tube.
Okay.
All right, here we go. Already, it's halfway there. Well, one more. I think you should do it. There you go.
I did it.